Okay, one of the things that I've been wanting to talk about is when we are not connected to what we think of as an ideal utility service. Okay, to this point, we have been assuming that we are connected to a perfect grid. And we call that grid is usually referred to as an infinite bus. So if you ever hear that term again, basically it means there's zero impedance between us and the utility, or us and the utility grid or the system. Okay, but it's not perfect. And what happens is if you ever have to work on a project like this, what you do is you contact the serving utility and you ask them what does their system look like, looking up in to the electrical grid wherever your meter's at. Okay, and when you do that, they're going to give you three components. They're going to give you the system voltage and line-to-line voltage. They'll give you the available short circuit current, and they'll give you a strange thing. You're going to think the X over R ratio. And if you think about it, impedance makes a triangle. And so what they're doing is actually giving you the tangent of theta when they give you that X over R ratio. So let's work through an example here. From this information, we can work backwards then using the single-phase equivalent model. When we're using the single-phase equivalent model, we have to convert the line-to-line voltage to the phase voltage. So we do that. We draw a real small system where we got an R and an X. We'll call it R system and X system. We short-circuit it, and we allow that short-circuit current to flow that they gave us. And then what we can do is we can calculate the magnitude of the impedance, where Z is equal to R sys plus JX sys. Okay? So we can get the magnitude of Z. And once we have that, we see that Z makes is actually a right triangle consisting of R sys plus JX sys. And then theta is equal to the inverse tangent of X over R. Then from this being a right triangle, we can calculate R equal to Z cosine of theta and X equal to sine Z sine theta. Those turn out to be in ohms. Okay. So here's an example. So we called the utility company. We said, hey, we're at so-and-so an address. What does your system look like that serves this property? And they tell us that the line-to-line voltage is 34 kV, the short circuit current is 6,175 amps, and the X over R ratio is 2.65. So from that, we can calculate the phase voltage and the magnitude of the impedance. Now, what I did was I envisioned a single phase equivalent model where I had R and X, R sys and X sys, and this is a J. Then I short circuit it, and if I short circuited that, the short circuit current that would flow is the 6175 that they gave us. So this is then V phase. Okay, so then the magnitude of that impedance is 19.9 kV divided by my short circuit current of 6175, or 3.22 ohms. Theta is the inverse tangent of the X over R ratio. Turns out to be 69.3. Then I can plug those into these formulas. So R is 3.22 times the cosine of that angle, 69.33. And I get 1.14 ohms. Important to remember that these are now ohms. It's not per unit ohms, it's ohms. X is given as 3.22 cosine of 69.33. Okay. Then we take these and we can put them into the per unit system. Okay. Where we take the actual R sys divided by Z base and X actual divided by Z base. And Z base is going to be our utility voltage, in this case, 34.5 kV squared divided by S base. for whatever system that we happen to be working at. Okay. I hope all of that makes a lot of sense. This is actually a pretty powerful tool. And what this does is gives us a way to represent the utility system. So looking in our terminal, so we can take into consideration the actual non-ideal characteristics of the utility grid. Now, our sys and xsys vary, I would say, can vary wildly as well. When I talk to the utility companies, they tell me it doesn't, but there's a lot of switching and paralleling of circuits and all that kind of stuff that goes into that. But they'll give you real current numbers if you call them. I've done this several times.